Hello, everybody, and welcome to our Python for Finance online bootcamp. It is the second session. We have built the foundation, if you like, and now we are going to build on top of that. I think many people these days, when they enter the Python for Finance world, the entry is often via NumPy or via pandas, but Python in and of itself as a programming language without the third-party packages is already pretty powerful. This doesn't mean that whatever you can do more efficiently with pandas, let's say, should be done primarily with Python without using pandas. No, that's not the case. But there are, I guess, a couple of idioms, a couple of ideas, quite a bit of background information that is useful no matter what you do, no matter what package you use. So in that sense, I usually don't skip the basic Python part with the data types, the data structures, and also the processing of data with pure Python, because you'll learn quite a lot, I think, in this context, which you can then apply as well later when you then enter, let's say, areas of like data processing, pre-processing, etc., with pandas, let's say, well, the machine learning arena, etc. So in that sense, we have now the foundations together. Of course, not all of what you could learn or what is important in this context, but quite a bit. And we will see, I guess, that we can benefit throughout of what we have learned so far. In that sense here, Python infrastructure, tools, idioms, data control, think in terms, for example, like of list comprehensions. We've dealt with data, we've used control structures to process it. We have worked and seen a little bit of IPython. We've worked more intensively with Jupyter Lab. We have built the infrastructure from scratch within a Docker container using Ubuntu as our Linux operating system today. I'm going to enter the cloud arena, and I will repeat what we have been doing before within a Docker container in the cloud. Again, like with the Docker container, it's not absolutely required, but it's something that at least should be of interest to you. Maybe if not for now, then in the near future, because dealing with containers, dealing with cloud infrastructure is something that is simply very important these days, not only when you want to do Python for Finance, in other areas for sure as well. If you use the link that we have provided here in the gist, when you follow that link, you get, I just noticed, maybe somebody can confirm, that they now even provide $200 free credit. Used to be just like, I don't know, 25 or something, right? And then they increased it to 100, and now it's 200. So I'm pretty happy for that. Where we share our affiliate link, that you get the benefit of free credit, which is, I would say, pretty good to get started with, because you can even work with larger cloud instances. You will see what options we have there without paying a single dime in this context, right? So that's for context for today's session. Once we have the setup up and running, the goal will be again to have Jupyter Lab up and running, password protected, so I don't dive into the details, for example, of SSL encryption, since it's running on a remote server. I mean, we are here in a bootcamp, which doesn't allow us to go into every single detail that might be of importance in our much more comprehensive program, where have 250 plus hours of instruction. This is something that we come in detail, but we focus on the very basic, on the core of the core of the single topics here, right? And then today we are also going to enter the statistics arena with, let's say, regression. We do some Monte Carlo simulation and proper financial applications based on NumPy. I would say that NumPy is at the core of, if you like, quantitative finance, pandas of financial data science, I would say, and also algo trading and a few more. But the two of them together are pretty powerful. Of course, we have Matplotlib for visualization and a few others, but this is what we are going to focus on, and Matplotlib will be accompanying us throughout for any type of visualization. Yeah, just maybe a very quick reminder for those who just enter. right? So the guiding principles for the bootcamp is Python first. So it's not a theoretical exercise. It's about Python. It's about coding. The examples are specific, right? I'm not intending to provide any kind of exhaustive overview. Whenever we deal with data, we work with static data sets, like in the previous session, so that all the results are reproducible for everybody without using credentials for APIs or whatnot, and it's practical, right? If you think for yourself, what is the best thing that I can do? Is, yeah, I would say get started with repeating what we have been doing, then repeating from memory what we have been doing, then asking yourself questions that are of interest to do, and trying to implement this on your own, right? So it's practical. It's about practice. My example was learning how to play the piano, right? So I'm aware of, this is the upper left-hand corner, that there are different levels of skills for people that follow us in the bootcamp here. Some might think, oh, well, this is so simple. Others might think, oh, this is the first time I see that. That's kind of like, I would say, the nature when you have that many people signing up for such a bootcamp. I do everything on macOS, but overall it should be implementable on any other machine. That's also, among others, the reason why I used from the outset Docker containers, which you can use on every platform with Linux, as well as the cloud, which you, of course, can also access and set up from any operating system. The examples are opportunistic here and there. I go left and right. I have, of course, my plan in the back of my head, but I'm still open if there are a few questions, and let's say informal voting, we can still change course as we go. So it's not fully random as the dice might suggest, but it's opportunistic. Delayed rewards. Not everything that you see, that you encounter, might be immediately completely clear, and you might not immediately internalize everything that we do. Just think of it like an investment. When you invest today, let's say in a stock, I don't know, one of my running examples obviously is Apple stock, right? You wouldn't expect tomorrow to have kind of like a 20% return, right? This is something that usually comes as a delayed reward, delayed profit, delayed return. And I think you should see what we do here in the same fashion, right? So let's get back and let's restart with the infrastructure. And I just got a confirmation, because for me, when I provide affiliate links where you get free credits, of course, a little bit difficult. I will need to sign up with different email addresses, etc. You know the procedure. So I just got a confirmation that it's indeed 200 US credit for 60 days. And I think that's really fantastic. Happy to be in a position to provide you with such a starting credit. And speaking of that, I now dive into the world of DigitalOcean. So when we go to the main starting page, I like the slogan here: dream it, build it, grow it, right? And we use it since years. So we have been using it while DigitalOcean was growing. It's by far not the biggest cloud provider. You know, the big players for sure, AWS or Microsoft Azure, etc. But I think they are, from a cost benefit point of view and from the simplicity of setting your stuff up, they are, I think, unbeatable. There might be others, it might be a little bit cheaper, a little bit here, a little bit there, but over the years, also with the hundreds of people that have been following our program, people have been overall, I think, pretty happy. Here the pricing, simple, predictable pricing. I mean, this is of course marketing, but it is indeed, right? So with the virtual machines, you start at $4 per month. Now put this into relationship to the 200 US. You can run a couple of them for 2 months with 200 US. Yeah, you see that there are different, how shall I say, categories of resources that you can book, but droplets is what we will be focusing on. And there are basic droplets, right? When you go further down, general purpose droplets, CPU optimized droplet. You see, there's a large selection, but yeah, don't be irritated. Probably when you get started out, you probably wouldn't look here at 192 gigs, 24 CPU, etc. option, right? This is probably not what you're looking for. So for us, something like a general purpose droplet, where we have, or here, even the basic droplets, that's absolutely enough, like 2 gigs of RAM, maybe 2 CPUs, that's an option that I'm choosing since years, right? So 18 US per month, and you're good to go. 2 gigs is fine, 2 CPUs is fine to get started. If you have a higher workload, you see it's pretty easy to scroll down and here to scale it in the basic part, even to 8 CPUs and 16 gigs of RAM. But I don't want to here play the salesman for them. I just wanted to show you have a large selection, and that's indeed simple, and the pricing is predictable. The predictable pricing is simply as it is, but that it is simple as well, I want to showcase right now. So recall that Q&A, etc., is going via the Discord server that you can use anytime. And you should have the link if you have the link to the resources. And I'm having, whenever I look to my left-hand side, this indicates that I'm looking at the questions that might have popped up in the meantime. So I'm here in my account. This might look a little bit different for you. So I called here a project, as they call it, tools and skills, what we use, for example, for our program. And I don't want to go, let's say, on the meta level through it, but once you have such a project, you see here the create button in green, and then you see the resources now without the pricing, right? Here the first element is a droplet, and this is the cloud instance. When I click on that, you get the overview screen here, right? And the first thing that you see is choosing the region, obviously via the IP. DigitalOcean knows that I'm sitting here in Frankfurt. I could also choose London, Singapore. I mean, you see the selection here, or Bangalore. They say either you should choose a location which is close to you or close to your clients, right? I might now choose indeed Frankfurt because I'm just like 190, 200 kilometers away from Frankfurt. I don't know exactly what a data center is, but roughly like this. Let's say 200 kilometers away. Everything else would be much further away. So data center here, right? And here's what I say: select the data center closest, etc. Now we can choose an image, which means the operating system. I will go with Ubuntu, what I had with the Docker container, and here the version, so it offers me the latest version. You see there's 2204. LTS means long-term support. That's the latest version that they offer here, right? I did my testing already. It took quite a while until it was updated. Maybe I go with 2204. From what we are going to do, this shouldn't make a difference. Just the updating, upgrading on the server, this might make a difference, but not what we are going to implement. Now you see the droplets here, the shared CPU, the basic. I said that's okay, right? Here are the others, the more powerful ones, premium Intel, premium AMD. I go with the regular one here, and I chose the one that I mentioned before, like 2 gigs of RAM and 2 CPUs. This costs like 18 US per month. Let's say for me as a German, as a European, this is roughly 50 cents, euro cents per day to run such a cloud instance, right? I don't know. Somebody's asking about audio. As far as I can tell, it should work. At least go to webinars indicating that it's working. So I will have a look at the audio, but go to webinar. Shows me here in green, orange, or red whether it's good or bad. And sometimes indeed you might have on your end maybe some issues, but as far as I can tell, this should be good. So 18 US per month. Feel free to choose any other option with your free credit. So need more disk space? No, I don't need any more disk space. Then we need to put it H key here. If you don't know how to create it, how to put it here, there are very good tutorials on the DigitalOcean webpage, right? You see here we have a bunch of SSH keys that I can use. Now I'm working on the Mini 1. That's a Mac Mini 1, right? I would say this is another selling point. I mean, you can, of course, because it's public access, if you, let's say, go with AWS, you also can read the tutorials of DigitalOcean because they are well written, well maintained, updated, etc. Right? But I mean, the overall package, I would say, the pricing, the value that you get from pricing, the speed and the simplicity, for me, make kind of like a consistent package. If you don't want to work with SSH keys or you have never done so, you can also choose a password. And later on, when I log in, you would be prompted, for the password. Right? This is also an option, but it's more secure to use an SSH key. Right? The rest here is more sophisticated stuff, not that interesting. Here I can give it a name, Python for Finance Bootcamp, let's say, so that we know what we are dealing with. The same that I've chosen for the Docker container, and I do this purposefully, right? And without me speaking and explaining a couple of things here, this is a matter of seconds to go through. This doesn't take 30 seconds. If you have done it a couple of times, you go, oh yeah, that droplet, here and there, a location droplet, operating system name, and you're done, right? So this is really a matter of seconds. And the creation, I don't know if they still communicate this, but back in the days when we got started with cloud instances, of DigitalOcean, they said it takes 1 minute to fire up a cloud instance, and the 1 minute is what I still have in the back of my head here. Sometimes, I must say, from experience, it takes a little bit longer, but usually not that much longer, sometimes a bit faster. I would guess that it depends on the traffic that they have on their page, on their infrastructure, right? And if you wonder, for example, our Quant platform with all the video servings, etc., everything that we do these days is run on DigitalOcean. So we don't use it only for teaching. We run a ton of Docker containers, separate cloud instance workers, as we call them, for Jupyter Lab for our students and delegates, right? Including the video serving, etc., via DigitalOcean. Pretty, I would say, also in that sense, safe, secure, right? High reliability, and I would say, as I said before, for us now speaking as a company CEO, also cost benefit case is absolutely there. So I've copied the IP address. That's now important. You cannot know upfront before you fire this up what the IP address is, because this will be unique. I've copied it now, so when I hover over here and click copy, you see copied. I have it now in my clipboard, and the next step is that I go as I did with the Docker container. I go now here on the shell, and when I show you my other terminal, so here my Docker container is still up and running. So from the previous session, I didn't stop the container or whatnot. This is still up and running, right? So it doesn't hurt what I'm now going to do. I just use another terminal, right? And I now need to SSH secure shell as a root, and then I paste the IP address here. This is the unique address. You can think of it like an email address, but of a server, a unique address like country, city, street, and street number. Right? So it's not like this. It's not the organization, but I just wanted to make an analogy here. So when I execute this, it probably asks me whether, I have never connected to this server. So it now asks me, am I sure that I want to connect? I say yes, and it now prints out a bunch of things here. Expanded security maintenance is not enabled, a couple of stuff. This looks now quite a bit different, but overall down here it looks like, let me clear up the screen, it looks like within the Docker container, root at pffbc, and indeed we have the, when I go one level up, we have the typical structure of the Ubuntu Linux operating system, right? And this is now not on my machine within a container. This is now in Frankfurt in the data center, and I'm communicating now with the server in the data center in Frankfurt. I'm going to the root server, and you see there is just like a, I would say a leftover folder here, nothing else, right? And as we did with the Docker container, I do some housekeeping, update. So to update the package index, right? This takes a bit, not that long, right? And here we see already 48 packages can be upgraded. So I do this usually. So there wouldn't be a need now necessarily to do it, but usually we would do it, upgrade. Then it again communicates. Now it says 241 max of additional disk space, etc. And I say yes, and it now retrieves the latest and greatest packages. Hopefully greatest, at least the latest. You might recall how this looked within my Docker container, and in the Docker container, the Ubuntu version was kind of a minimal version, so not that much was installed. So here on the server, you can expect more to be installed. When you recall, I installed the little helper tool wget. Why I install wget? Because not even such important tools have or are installed in the image that I use with Docker usually. But here, for example, I would expect to have wget and many other tools to be installed. But for a Docker container, this makes sense because the use case usually is different. So newer kernel available. Okay, so I simply go with the defaults, and we are good to go. Update is done. Server and services have been updated. So for example, when I say I would expect many Linux tools already to be there, for example, HTOP is a resource manager, and it allows me, so HTOP, it allows me to inspect the resources of my Droplet, which are fired up. And this, if you like, enables me to check whether indeed I have two CPUs, and yeah, here is CPU 0 and there is CPU 1, and also the memory. So I booked two CPUs and I booked 2 gigs of RAM, and this is what I see here. Apart from that, below that, you see the current processes running. So without me executing a Python script or whatever, there's already quite a bunch going on. Right? For example, me communicating with the server and a few other background processes that are running on the server. So with F10, I can exit. And when I now execute here Python, it says no, it's not there, but for example, Python 3 might work. So let me check Python 3. Yeah, Python 3 is there. So with the Ubuntu server from DigitalOcean, I even get Python, right? So Python 3.10.6. But I don't know what the people who have created the image have installed, what they have configured. So I can check, for example, import NumPy as NP. This is not there, for example, as one check, but I don't know. So I would need to go through it. I would need to check what is there. Therefore, in general, I would basically do the very same thing that I did within the Docker container in the previous section. So I would download the Miniconda installer, and then I would start from scratch and install my own Python over which I will have full control. So that's typically the plan. Let's get started with the Miniconda web page. You recall I used the installer for Linux with Arch architecture for my Mac M1. So Apple Silicon, as they call it, like here, right? But now, since I'm on regular servers, no Apple, no Arch processors or whatnot, for sure, no Apple Silicon. I can go with the standard Linux 64-bit installer here, but it's Linux. Obviously, we are in the Linux Ubuntu world. So copy link address as I did with the right click. Basically, I can already close that page. I only need it for the link. And now I would go with wget. I needed to install it. Here I would expect it to be there, to be pre-installed. That's the address for the hopefully right installer, and it's going lightning fast. When I was downloading the installer to my Docker container, this was retrieving something from a server and downloading it to my local machine. Here I'm just providing instructions, if you like, on a remote server, and the remote server downloads it from another remote server, and you see the connection is pretty fast here. It was running at 300 megabytes per second. So I have now the installer, and as I did before, bash Miniconda is the execution command. With return, I get started, go through the licensing agreement that you should read carefully, and I accept the license terms, yes, and I also go here with the default location for the Miniconda installation. This all, I would say, looks more or less exactly the same as we have been doing it in the Docker container, and so we have a few synergies in terms of, like, no matter whether we are working locally with the Docker container, Linux, Ubuntu, or remotely, should be more or less the same. I say here yes, as I did before, to get the Conda initialization. Here, as before, I need to restart bash in order to have Conda ready. You see the change in the prompt, and now we are in the base environment. So Python is there. Just for confirmation, 3.1010, a little bit later than what we have found there, but as in the container, no IPython, at least not in the default Conda installation. But I want to now dive immediately into the Jupyter Lab world, Jupyter Lab. And what we also had was matplotlib. I can do this here in a single step. When I install Jupyter Lab, matplotlib. It communicates with the server of Anaconda Inc. And it will prompt me and ask for a confirmation. Yeah, yes, I confirm. Exactly what I want. I didn't check every single package. What I'm installing is already a bit. Particular Jupyter Lab has a ton of dependencies, we can say. I just asked for Jupyter Lab and matplotlib, and you see the pretty long list here, the pretty long list of packages that have been installed, and it's still not finished here. So it's now starting to get ready for the installation. And we are there. So the IPython tool is there because it gets installed with Jupyter Lab. So I didn't need to write conda install IPython in Jupyter Lab and matplotlib. So here, without me typing out IPython, it was installed, right? So import NumPy, for example. Oh, it's already there. It was installed with the packages that I've installed, probably with matplotlib. Import matplotlib. It's also there. So you see, we have now already a bunch of things installed here. IPython, but I want to, as I did before, primarily work with Jupyter Lab. So this is what I want to start out with. Yeah, and there is a good question related here to my import of matplotlib. I would say that matplotlib is indispensable for plotting in Python. Of course, there are quite a bunch of alternatives. Bokeh of Anaconda would be one. Plotly in combination with couplings, which I use since years, it's wonderful. But for the base visualization task, I think matplotlib is indispensable. And yeah, let me, for example, use case, me writing a book, let's say, or a tutorial, or somebody writing a blog post. In general, you would like to have static visualizations, and they are, I would say, still better prepared and saved and used via matplotlib. Of course, interactive graphs with Hoover effects, etc., they are nice. I'm a big proponent of that, but yeah, it is on top of what is there in the basic stack, and matplotlib is the basic or part of the basic stack, not of the expanded one. So Jupyter Lab was a goal. So the first thing that I do is provide a password, as I did before. Again, I'm not going into the depths of securing the communication, which you should do for real applications with SSL encryption. Right now that I'm communicating from a local machine to a remote server, the communication should in general be encrypted. But this would entail creating certificates and a bit more of a configuration, which we don't simply have time. It's also not the primary focus. But what is a quick win, a low-hanging fruit, is to add a password so that only you with your password. The alternative would be this long token that we have seen in the Docker related context. This will be the alternative, but proper passwords usually are preferable because you can recall them and they should be safe, of course. Here for the illustration, you might have noticed I didn't type that long, so it's not a long one nor a secure one, but at least you would have a difficult time to guess. I will comment in a second a bit more on this. So now I'm going to start it. Jupyter Lab, like I did before, allow root. This is now really a topic that you should be aware of what you're doing, because again, this is now on a remote server. And whoever gets access on Jupyter Lab, which will be running on this remote server, is able to access everything, every single corner of your server. Therefore, be really, really careful and read the instructions on the Jupyter page, how to set up maybe another user. This can also be figured out via the tutorials of DigitalOcean with a different user, which is not a root. You would then use SSL encryption plus passwords to make your Jupyter Lab running on a remote server as secure as possible, or sensible if you like. So allow root, that's dangerous, but we are aware of the dangers. I don't have any confidential material on the server, basically I have nothing there. Then the IP address 4 times 0. I don't need to specify the port, but for doing it explicitly here, I can, let me go with the 999 that I have chosen previously. By default, it would be 888, but here I go now with the port 9999, so that we have here a bit of a consistency and a connection to our Docker story. So let me execute this and look what happens. So we still see here the command that I've used. Here a bit of an output, and down here the important part. This all looks good so far as I can tell. Right, it looks good. And now you might ask, how do I connect to it? This here won't help you any further. This is more or closer to what we need, but it won't work out of the box here. So let me copy this here and let me put it in the line, but this won't work because my Chrome doesn't know what PFFBC is. DigitalOcean, here the server knows what it is, namely this is the IP address here. I have called this PFFBC and here's the IP address, but my machine, my local machine, the Chrome browser that I'm using needs the IP address in order to be able to communicate with the remote server. So I need to replace here PFFBC by the IP address. And this now suddenly let the dialog for the password here appear. You see, this is not really sophisticated in terms of multiple users, etc. There are other options as well, but here it's plain vanilla Jupyter Lab, Jupyter Server, as you see in the tab header, right? And at least it is password protected. I say never, and I'm good to go here. So it's up and running. You see here, because we are not using encryption, it says not secure. So your connection to the site is not secure. So be careful, therefore, with exchanging confidential, maybe client information or your proprietary trade secrets via such an insecure connection. For me here, for the sake of illustration, I think that's justifiable. So I have now my third instance here. So I have my local Jupyter Lab up and running. I have my Docker container locally, but Ubuntu up and running. And here there is now the Droplet, the cloud instance version up and running. You know, I'm a big fan of the dark theme, as easy as that. You see here Miniconda 3, that's the Python installation. This is what we have installed. There is the Miniconda installer. Basically, this is not needed anymore. I could download another installer or could download it anew. But once we have Miniconda installed, we can also safely get rid of it, because this is something we can always get anew from the remote server from Conda. Yeah, somebody asking with regards to the service to the ports related to the mapping Docker container and outside world. When you use like two different ports, be careful. So time does not allow to go here into the details, but I would recommend that you work with the default values that I have provided you with in the Docker container call, like 9999:9999. This maps the internal 4x9 to the external 4x9. Whenever you choose different numbers there, you need to be careful. What is inside, what is outside, etc. And is, for example, 4x8 already used by another process, etc. So go, my recommendation for the beginning, with the basics, with the default. Once you feel confident, you can then maybe check how you can adjust that. So we have the Jupyter Lab up and running. There should be matplotlib, and we have seen NumPy as well. Maybe let's upload something here from my Bootcamp, for example, the one and the other one that we have used previously, and I have now uploaded two files. So with the Docker container, I was able to mount a local folder to the container. This is not possible now because we are dealing with two different machines that are, as I was pointing out, 200 kilometers apart. So here I need to upload the files, but they should work as they did before. So you see, this is the state of this Jupyter notebook, which is also on the gist. And when I now say run all cells, you see that here it simply executes. For the first one, that's not a big surprise because there's just plain vanilla Python, no matplotlib, nothing special. So let me now do it for the second one where we do plotting, etc. So run all cells. And here with the data that we have processed, that we have worked with, etc. So this works in the same way. So no new code. You notice I'm just checking whether my remote server with my just freshly installed, from scratch installed Python installation with Jupyter Lab and Matplotlib is running and working as desired, and it seems to be the case. So the last things that we did was here to visualize as a histogram the log returns of Apple and the comment that this is not normally distributed because we have fat tails and high peaks. So that was the final story and case that we had. So on the server, and you see this is all but magic. There are a few things that you need to internalize, a few, I would say, minor skills. They are not like the biggest skills in the world, like playing a piano or playing the violin, right? That's something else. But here to deal with the basics of a remote cloud instance, that's really just a couple of things that you need to recall, or you look it up, or you write it down for yourself as a checklist, for example. That shouldn't be a big not that much of a big deal. And I hope that this is something that you agree with me, because many people say, well, I've never worked with cloud instances. I'm afraid of not being able to learn all of this. It is not that difficult, and you have many benefits. For example, those of you who are interested, let's say, in algorithmic trading, if you want to deploy an algorithmic trading strategy, I would recommend that you never ever in your life do this from a local machine. You should always do this with a remote cloud server, and we emphasize this in our program as well, and show like tips and tricks and techniques, tools and skills that you need around that in order to make, let's say, an automated trading strategy quite a bit more robust and reliable as compared to running it on a local machine, where you might have issues with your internet connection, where there might be electricity outages, where there might be fire, rain, floodings. I don't know, you have an emergency and need to run with your notebook. This is all a no-brainer when you run your stuff, which should run maybe 24/7 then in the cloud. All right. So that's for it for the cloud. I hope you will test it for yourself. If you haven't done so, I recommend it intensely. So please do it. Do yourself a favor. You can only learn and benefit from it. I'm now not going to work further in the cloud. I could do that, but for convenience and for me to be able to push what I'm coding afterward, step by step to the gist, I go back to the Docker container because otherwise I would always need to download the file and then put it in my local folder and then push it to the gist. So this is for, let's say, convenience and as well as security reasons, because I have everything that I do also here in my Dropbox folder, which gets backed up as soon as I click save or save a file. So far, I don't see any additional questions, which for me is a signal to move on and now enter the world of NumPy. 03 here, IPython, I still say, since I'm old enough to have experienced that and long enough in the Python ecosystem, IPython notebook, as it was called, it's of course Jupyter notebook, but the ending IPYNV, it's still the one in place, but I didn't change it. And within this empty Jupyter notebook, I now want to get started working with NumPy, right? So here the NumPy package. So let me try to import it. Import NumPy SNP, and it works like on the server, because when I installed Jupyter Lab Plus, in particular Matplotlib, NumPy was installed there as well. So I have the package available. And you might now ask, if you haven't had that much experience with NumPy, yeah, we have list objects, we have tuples, we have dictionaries, we can process data. Why a package for, yeah, if you like, arrays? And arrays are generally collections of objects of the same type. So when you recall, we had the list object, and this holds true for the tuple, and we were able to put in integers, floating point numbers, strings. We could even put list objects into list objects, etc. So basically almost full flexibility, I would say. Right? With NumPy, the question is, why do we have here a package which is dedicated specifically towards ND array objects? So that's the name that we should internalize. ND array means n-dimensional array object, and that's really like magic if you are in Python for finance, I would say, and in many other areas. So let's get started before we get too theoretical and too abstract. Once we have a couple of examples, let's say we talk about animals in general, yeah, that's nice, and we can talk about for hours on end. But let's get down to the lion or to the bat or whatever animal jumps to your mind, and have a look at it, analyze it, and try to figure out the differences to the other animals that we might know. So when I have something like a list object, like here, where I say 1, 2, 3, 4, 5, right? I can construct this in many different ways, like with a range object, etc. This is as we know it. We can add elements, we can pop or drop elements. That's our list object. We have already gained quite a bit of experience. We even have imported thousands and thousands of quotes for different financial instruments such as stocks index, volatility index, euro, US dollar, etc. So list objects can do all that. But now let's see how it looks as an array. So when I now transform this, this would be one way to create an array as NP array of L, and this gives me now an array which from the outset has only one major difference, and it is that it says array, but you see here the inner part looks exactly the same as we have here. So that's now a completely different beast. And when I say beast, one of my favorite words you might have noticed, I mean a different type of object. So here we have a list object, and type of A is now a NumPy ND array, and here you see it, ND array object, n-dimensional array object. Here it's just one dimensional, but we will see other examples there as well. So what can we do with it? What is now the benefit of having that? Yeah, let me get started with what I would consider one of the absolute major benefits from a mathematical financial point of view, and that's vectorized operations. So it's not what I typically introduce first, but I want to come now with a sledgehammer instead of like a screwdriver. So when I do something like 2 times L, and we have seen this in action, we get 2 times the content of L as another object which has twice the length. When I do 2 times A, this is now what is called a vectorized operation. So this is a vectorized operation because it works like in linear algebra. This is a scalar multiplication. I think at this stage I can even zoom in a little bit further because we are dealing with very small examples which are not necessarily connected. 2 times A, vectorized operation. Right? I can also do L plus L, also something that I have illustrated. Adding a list object to a list object gives me, as before, twice the content of the original list object. Here, when I do A plus A, so the array plus the array, what do I get? Yeah, I get here again, mathematically speaking, element-wise addition. Again, so I won't write it out for the next 20 examples. I don't know. Vectorized operation. This is here element-wise addition. So this is how you would add 2 vectors in linear algebra. The first element added up with the first element of the second vector gives the result for the results vector, and second element plus second element, third plus third, etc. I think you get it. And so these are now the first pretty simplistic example. We will see these operations on a relatively large scale in action where we get real benefits out of that. So vectorized operation, element-wise addition. So we are here, if you like, in the numerical world, and this is where NumPy, the name, comes from. It's numerical Python. While list objects don't necessarily expect you to pass and to use integers, floats, or whatnot, you can use strings, whatever. Here in the NumPy world, I would say the default use case is to deal with numbers, and typically with large amounts of numbers, be it one-dimensional, two-dimensional, three-dimensional, or even higher dimensional. And the ND array object is optimized to efficiently implement the operations from a syntax point of view, as well as from an execution from a performance point of view. I come to performance a little bit later. So that's the ND array object with a vectorized operation. Now let's do a few more tricks with the ND array object. So we can do other operations like division here. We can go with the exponent, right? So the squares now of the values. We can do something like 2 to the power of a, for example. We can even go a to the power of a. This also works. See, full flexibility, if you like. Not everything is possible, but many things are possible, as you see here. And this all defaults to sensible mathematical operations and results objects here, as we can tell. And then we have a bunch of methods methods and attributes here. I don't want to go through all of this here. Pretty nice stuff, but I want to focus here on the calculation side. So for example, I can calculate the sum via the method. This is equivalent to sum A, right? Or to sum L. This works as well, right? So sum works on the ND array object as well as on L, but we have the method, and I come to that later. So what we don't have out of the box, you might have noticed that it was quite involved to calculate the average of the euro-US dollar quote for our 2,609 or whatever observations that we had in the data set. So we needed to collect it, transform the data, and then to sum it up and then divide by the length. For example, here we have also methods that are statistically inspired, like the mean value. This gives me the average out of the box, so I don't need to implement the formula for the mean value. It is there. Or also statistically inspired here, the standard deviation for the values that are to be found in there. I mean, we will see quite a few more. Let me know we don't have. I would need to check what I was looking for. There are two worlds or two separate buckets, if you like, from which we can choose mathematical functions here that we can implement on a numerical array. And the one that I've chosen here are the methods that are attached, and the other one are what are called universal functions. Here I have something like NP square root of A, which calculates the square root for every element, or NP the exponential function. So it calculates element-wise the exponential value of the elements here, right? And gives me a results object of the same size, and quite a few more. I also have things like here the maximum, right? That I can choose over A, and quite, I mean, it's we cannot go through all the elements that we have, but you see how it works. We have this object has methods. On a basic level, we can implement vectorized operations. We also have what are called universal functions here that I can apply on such a NumPy and the array object. The on a basic level here, when we think through what we have discussed, data types and data structure. In the data structures that we have discussed, we were able to put in different elements of different types. So we had integers, floats, and strings, for example. Here, and this can be looked up via the dtype attribute, we have, and this is for the regular ND array objects, we have a single dtype. So this is, if you like, a constraint for regular ND array object that we need to specify one dtype, different to the list object, different to tuple, different, if you like, to the dictionary as well. Then we have also something like size. Here where we get the size, meaning how many elements we have. Right? So there is now a bit of meta information, and there is more that we could figure out. But I think that's enough for the very basics. You should recall we have it's basically four things. We have the ND array object with a vectorized mathematical operations. Think of linear algebra. Then we have methods, powerful methods that we can call. Then we have the universal functions, and we also have a bunch of attributes that we can look up. This is a pretty simple way of thinking in terms of what an ND array object is all about, but I think it's a good starting point. So in terms of creating an ND array object, I now want to show you other ways. Like here I can go with B, for example, and set something up like this. This now gives me an ND array object with 10 elements where every element is 0. Right? Where every element is 0. There is another one like this. This is with 1. So I can create an ND array object here with ones only. There's yet another one with empty, which now looks the same, but this might, when you go like in the billions of values, this might be helpful. So maybe I'll leave this out here. This is a little bit specific. Let's, for the time being, have a look at these ones. So let's say we have the B object as I have created it right now. We can now look up everything else. Like here, you see the way we constructed it, we ended up with a dtype of integer 64. Here, the dtype, you might have guessed it, we have the dots here. The dtype is float 64, so meaning 64 bits for every floating point value in it here. And when I say for every, this is again possible to be looked up here via size. And if you are interested in the memory footprint, you can always look up n bytes. And these two now together give the n bytes, meaning here we have 64 bits, which is 8 bytes times 10 elements gives 80 bytes. So this is an approximation of the memory footprint. There's a little bit of overhead, but it's just a little bit. There's not that much of an overhead involved there. So that's now for the construction here. I said that when we deal with NumPy, we will benefit from what we have seen or learned about indexing with regard to the strings or even list objects. We didn't do that much of a list indexing or whatnot, but let's see here how indexing works. So B0 is 1. Here is not a big surprise, but what I can do, for example, I can overwrite the first value by something like 10, right? When I now look up it here, and this is a mutable data structure, so the number of elements is fixed, but I can change the value. So b of -1, the last element might be 20, for example. So I end up here with the last element changed, right? So that's again another way of constructing it. We see here the indexing. We also see that we can assign to every position another value. We can also do more sophisticated slicing, like the first 5 elements, let's say, or like here the final 5, -5 until the end. So all is possible, and again, the hope is that the indexing is consistent throughout the Python ecosystem, and overall what we are going to do, the indexing is consistent, fortunately. There are places and constellations where we might be careful, but the indexing, and this will hold true for the pandas data frame objects as well, but here for the ND array object, it works the very same way. So let me maybe do a little bit of structuring here, right? So that's the one, and here I go with 1D array objects. So this is just one dimension. When we talk about n dimensions, yeah, there must be a bit more. For example, a second dimension. Therefore, I do the structuring now. 2D array objects. And I don't want to repeat everything now, but I want to show that it's as simple as straightforward to work with 2-dimensional and the array objects as we did it here. So another way of constructing and the array objects is to use arrange or linspace. These are also 2 standard operations. So NP arrange, and this not only looks like the range 10, it's similar, but you see we get here now not something, a generator that we can iterate, or we get the object itself. So from 0 to 10 excluded, so just the 9, for example. And when I change this a little bit, like here 15, and I say this is now my new C object, this will be that one. And in the next step, I do a reshape. The reshaping, now this is one way of doing it, like 5 to 3. So the 2 of them multiplied must add up to my 15 elements, and 5 times 3 is 15. So that I end up now with a 2-dimensional ND array object. So we have first row, second row, a third, fifth, fourth, fifth, and we have first column, second column, third column. Right? So with that ND array object, I can now do basically the same that I was doing before, like 2 times C. This is now a scalar multiplication, but not with a vector, but with a matrix. Or I can do C to the power of 2. This works, or I like that example because we always get large values, or C to the power of C. So the lower right value is 196 to the power of 196. So you see we are still here within the range of numbers that we can represent. So this seems to work as before, 2 dimensions, and we have seen something like the sum. Easy case, but now I want to show you a difference. See sum, we have an axis argument which allows me to calculate the sums via axis 0, and there might be an axis 1, you might have guessed it. Where we have here the sum via the 3 columns, so the first column, second column, third column, the column sums, and here we have the row sums, 3 columns, 5 rows. So this is from 2 dimensions onwards, something that we need to distinguish. So the axis, whether the first, second, or maybe even higher dimensions. So for most of the financial applications, we are dealing with vectors, so 1 dimension, or with matrices like here, like 2 dimensions. So this works, or C mean, same idea. Here over all the elements, and mean can also be calculated via axis 0 or axis 1 to this end. Then we have the square root, for example, of C. Same behavior. Results object is now simply a matrix. It's a 2-dimensional object. So this works, I would say, as expected. So when I say the analogy would be in mathematics and linear algebra, yeah, this is the behavior that we would expect by changing vectors to matrices. Works in the same way, right? So the construction, again, can work like this, where we get started with an object that we have, with the zeros, with the ones. Here I used a range, and there are quite a few more, like linspace. Oh, I don't know if you will have a use case for linspace, so I cannot show you everything. So just therefore I mention it to whet your appetite and to maybe Google this later on. So wonderful, this works 1, 2 dimensions, 3 we could move on as well, but I don't have a use case currently for 3 dimensions. Now you still might wonder, beyond vectorized operations and beyond 1 and 2 dimensions, are there other benefits? Yeah, and one benefit that I usually like to show kind of early is the speed advantage, speed comparisons, right? So when I go and do the following, I say something like L list of range, or let me do it more generally, like N, and I go with let's get started with 1 million numbers. So I can use the underscore as a separator here. And I say L range capital N. I have my list object, right? This is now, as we would expect it, from 0 to 999,999. So we might check how long it takes to create this object. So 81 milliseconds. Not that fast. Here I might show the first. Well, let me show the final 10. Might be a bit more interesting than the first 10. Final, just 5. So now they're in a single line. So these are the final 5 elements from this list object. And when I talk about speed comparison, I'm talking about things like calculating the sum of such an object. So here, 27 milliseconds, list range. Now with ND array objects, let me go with my A, and NP range would now be the equivalent of N. Let me also time it. 9 milliseconds compared to 81 milliseconds. So roughly 8 times faster. And the calculation of the sum, 6.4 milliseconds versus 2.7. So we see sometimes it might be the convenience, but it's also about the speed of the calculations. And when I here use just time, this doesn't give us a proper view. So I would at least should use time it, which will do it a bunch of times to come up with an average value. And you see this is much better, it's much faster, 4.54 milliseconds. now, and it has done 7 runs, 100 loops, so 700 calculations have been implemented. And here for that one, it's now doing the same thing, like hundreds of iterations. Right? And you see we are ending up here on the microsecond level, which is below 1 millisecond. It's a third of a millisecond, so roughly a third. So I'm not always coming up with the exact relationships, just orders of magnitude. And you see, indeed, it is orders of magnitude faster. It's a factor of 10, maybe 15, 17 here, factor of the speed up, right? And that's, I would guess, considerable when you think in terms of large-scale financial calculations, when you can speed up things by a factor of 10. I think that's really considerable, right? And maybe one more example, the the square root with Python can be calculated, and now I show you how we would do it in pure Python, import math. Let's say for all the elements we would like to calculate the square root, we would do something like this, a list comprehension, math, square root of x for x in L, our list object. When I do the loop here, time it, it goes over all the elements in L, takes every element, calculates the square root, and then puts it into the list object. So square root with Python, the final 5 that we had before, and we get here now the square root. Or here we can maybe go with the first 5, for example. So we get the result, but here you see the time, not but, and you see the time. When I would do this with NumPy, time square root NumPy would be NP square root of A. I think it was, yeah, A. It was simply A for array. And this shows me here 14 milliseconds. We have seen before that the single measurements are usually not really reliable. So let me copy the whole thing. We would rather do something like time it so that we get an average. And you see the average that I get here is already 3 times faster than my single measurement. So time it, it stands here for iterations. It has done here 7 runs. And you see this is more reliable because this is now an average of that many calculations, that many runs here. For the NumPy case, we see it's again on the microsecond level. Again, micro. So here it is more than 2 orders of magnitude faster, which means here more than 100 times faster to do the calculations with NumPy instead of the standard way here of doing it with the list comprehension and Python. You might now say, well, from a syntax point of view, it's not that much more to type. Right? Maybe I do the same here, that you see that the values are the same. The first 5, the values are the same, the results are the same that I get. But the speed simply is 100 times faster. And of course, if we want to do something in finance, we will probably choose the option that is the fastest. We could now discuss also things like memory footprint, etc. Meaning that there are cases where, let's say, a plain Python approach might be better from a memory point of view, but this goes now a little bit too deep. I discussed this in other contexts as well, in our program, in the book, etc. But for our purposes, when we are speed junkies, like we Germans would like to drive our fast cars, for example, speed is something everybody can relate to, right? 100 times faster, more than 100 times. That's something we can say, yeah, that's wonderful. I buy it. I love it. Right? So, yeah, this is beyond the vectorized operations and some other features. This is also one major benefit of working with ND array objects when we are dealing with numbers here in this case, and it's simply the speed of the execution. Right? So to now get into the field of financial applications, let us dive into the world of random numbers. Right? So random numbers. Now that we have discussed speed, let me also import the random module from Python. So meaning that you can draw random numbers with pure Python, that's for sure, but we will see that again NumPy has head start here and has some major benefits. When I want to create, let's say, again, my number n here doesn't need to be 1 million. I go maybe with 100,000 random numbers to get started with. I can relatively easily do it here with a random package. Random, let's say we go with standard normally distributed random numbers. I can draw. Oops, there was one random too many. I can draw a pseudo random number to be specific here via random Gauss, and that one is supposed to be standard normally distributed. So mean of 0 and standard deviation of 1. With a single value only, I cannot tell the distribution, right? The only hope is that it samples properly from a distribution. Therefore here 100,000, so that when I now go and random numbers with Python, and I do something like list comprehension to do this 100,000 times for nothing in range n. Maybe we can time this as well. If we are now in the timing world, we end up with a bunch of random numbers. So 0 point, so above 0, below 0, etc. Right? There's a question with regard to the recordings. The recordings are shared on the Quant platform. So when you register for the Quant platform, you find all the resources there. It takes a little while until we upload them, but not that long in general until we upload it on the Quant platform. If you go to the gist, you find links to everything that you need there. So random numbers are there, and we can draw them. That's pure Python. We see here the speed, but my major point will not be on the speed side. But now it's always nice to see the difference. With NumPy, random numbers NumPy time, I can do it as follows. NP random, now standard normal, and I pass in n. So pretty fast, feels like 10 times faster, more than 10 times, right? And I have random numbers here as well. Of course, they cannot be compared to these values because they are supposed to be random. So it would be a big surprise if, without everything being equal, we would see the same random numbers here. We draw here the random numbers with Python, here with NumPy, and this is, as they call it, the legacy way of drawing random numbers. The new way would be to do the following: import, from NumPy random, import default random number generator, and then you instantiate a random number generator, and this is now your friend. This code here would then change to the following code with NumPy, random numbers NumPy. Here, this is replaced by RNG. This is now the new way. This is also faster. Here, again, where we just do the timing once, the numbers are not reliable, but from all my measurements so far, the new way is faster. The algorithms that are used are supposed to be better in terms of the statistical properties of the pseudo-random numbers generated should be better, closer to the expected moments, etc. So we now have random numbers, 100,000 of them, right? So we visualize these random numbers. We know how this works. We need matplotlib from PyLab, import PLT. Now I do my configuration, PLT style use. Now the cryptic Seaborn underscore we 0. No, this was, here's the dash underscore 8. And I do the config inline. I don't know. Something, I don't know why it doesn't do the trick. Figure format, maybe there's a typo someplace that my, no, it works. I don't know why tab completion didn't work here. In any case, this runs through and we have done some plotting, and I don't want to introduce something really new here. I just want to plot now as a histogram my pseudo random numbers from NumPy. I can also plot the other ones, right? We know there is by default the bins set to 10. This doesn't look nice in general, so going with a 50. This looks, I would say, like a, let me zoom out a bit, like a normal distribution, standard normal distribution here in this particular case. I can also go with the Python values, looks the same. So I couldn't tell the difference here. And what I was saying, with a single number, we cannot tell from which it was sampled, but with 100,000, we should be on the safe side. Meaning that when I go and calculate random numbers from NumPy, the mean value should be close to 0. Yeah, I think this satisfies the definition. And here the standard deviation should be close to 1. So that's the first moment, and that's the second moment here. That seems to be nice. If we draw more numbers, maybe 1 million instead of 100,000, the values are even closer to 0 and 1. And when I redo the exercise here, I will get slightly different results. In the chart, probably difficult to tell, but here we see now values here slightly below 1, and here a little bit higher than before. So these are now our random numbers. With the standard normally distributed numbers, for example, I can create something like a random walk, which I can visualize, as well, right? Yeah, there was a question that I haven't answered because people are now typing questions in one or the other area in Discord. Hope to keep up with all of them. Yeah, I use the underscore. Again, this is here. This, let's say this is 10,000, right? So this is simply 10,000. Right, this is true. That's the same. That's just to show where the separators are. If you have long values, it's difficult to read sometimes. Good question. So let me maybe draw now random numbers here with RNG, as I did before, but not that many, standard normal. Instead of my 1 million, I now just go with 100, let's say 100, right? And I now want to do the following: PLT, plot random number, CumSum, and let's see what happens. Maybe let me first plot it without the CumSum. So we see random numbers here, below 0, above 0. This is like a fever curve. I don't know, right? Standard normally distributed, above 0, below 0, right? That's what we see here. But when I put a cumulative sum, this is a sum step by step here, value by value, we suddenly end up with something that looks like a random walk, right? So we add up one standard normally distributed value to the next, and you see first it increases, then it decreases, increases again, decreases. When I repeat the exercise, it might look completely different. Here it looks more erratic, or again, now it's on average increasing, right? That's now here the last draw. We can also draw multiple of these at the same time. Show you here, and I go with 5. Now I provide the different shape, and when I now do the CumSum, that's not what I would like to have. I would like to have the CumSum along axis 1, and we get now 5 different random walks. And you see, for me, it's like second nature, I hope, with dealing with these objects, one-dimensional, two-dimensional, drawing random numbers, cumulative sum, simulation. Because basically, if you ask me how I started out with Python, I would say, yeah, like everybody else, playing around, doing things. But early on, I picked a topic that was of interest to me, that was related to what I did in my PhD research, and topics that were of interest to me. And this was basically about Monte Carlo simulation and about valuing options, and in particular American options. And therefore, like all these simulation visualizations, this is something I've done in my life. Hours and hours, weeks and weeks, and it feels like months on end. And you see here, it's pretty simple and straightforward. From 1 row to 5 rows, not rows, columns, I should say, and from 1 random walk to 5 random walks here. Right? So pretty convenient, I would say. So we have reached a point where I would say, well done so far. We have added quite a few things to our tool set. So maybe let me restart and clear it all, so that I can push it to the gist, that you have the latest version. If you have not been following along, let me check for that. I now scroll down. Now this is the second Jupyter notebook, and here it's now the third Jupyter notebook with a NumPy package, 1D array objects, 2D array objects, quite a few speed comparisons, and the final topic that we have covered, random numbers, including some visualizations. I have, of course, I have here obviously another empty notebook that we are always ready to change to a new one. But this is a good point, I guess, to make a break of 10 minutes, so that we then in the final part can dig a little bit deeper into topics that I mentioned before, in terms of using Monte Carlo simulation, which was already the starting point what we have covered. And here in the overview, you see it, doing Monte Carlo simulation here, and apply this to a financial context where we value a a European option as well as an American option based on a quite sophisticated, nice algorithm, the Longstaff-Schwartz or least squares Monte Carlo algorithm. Right? We have the basics together, but we need to, let's say we have the technical and mathematical basics together. We now need to put the financial elements into the mix in terms of having the right dynamics for the simulation, plus the ideas behind the option pricing, risk neutral option pricing. Yeah, in that sense, 10-minute break. You see here my clock, and in 10 minutes you're back for second part of today's session. All right, let's get ready to apply our technical approaches to a real-world financial application, namely the Monte Carlo simulation of a stock price process and the valuation of European as well as American options. So let's get back to, well, the Docker container is here. My 3 Jupyter Labs open. Could do it in all the 3. I do it now from the Docker container, but need to push it, as you know, from my local machine to the gist. And here in this case, I'm now going to rerun everything above so that we have from the first line with all the imports, everything executed. Takes a bit, yeah, it takes a bit now when I start from the beginning, because we do all these timings, right? And when we do like 700 calculations of X, Y, Z, that's the reason why it takes so long. It's not that the single elements are that involved, but it's just the measurements that we do in between. So simulating a stock price process, right? So I could do this now basically with the end of period value only, but I dive right into a proper dynamical simulation. And I have a specific example in the back of my head. This is, for example, in my book, Derivatives Analytics with Python, a running benchmark example. It is from the original paper 2001 by Longstaff and Schwartz, where they introduced the so-called LSM algorithm, which stands for least squares Monte Carlo algorithm. So, and the world that they model has the following parameters. It's the initial value of a stock price, which is 36. And then we are going to value, I put it right next to it. We don't need it in the beginning, but I put it here. It's the strike price of a put option of 40. So it's an in-the-money option from the outset. The period that we consider is 1 year. Then we have an interest rate, R, which is 6%. So there were years, obviously, when we were close to 0 for the short rate. Now we have come a long way, I would say, back just today, another rate hike in the US, where we are closer, much closer to the 6% of the paper in 2001 than it was for the last 10 years, let's say. But that's not of importance, so we could work with other numbers, but I have benchmark values available, and this for me gives like a guideline. When we see numerical values, I can say, well, that's in the ballpark or that's not. Then we have sigma as the volatility, which is assumed to be 20%. So these are the parameters. So initial price, here the strike price, majority, short rate, and volatility. Then we're going to do the following. We will have a time crit where we model 50 time steps, and we're going to simulate, let's say, 10,000 paths to get started with. So 10,000 paths. So we now need a few helper values. For example, dt, that's the length of the time interval, which is calculated as t, capital T, 1 year over 50 interval. So we have, not 50, I write here, m, that's a 50th, 0.02. So this is something that we need, right? And the next thing is that I'm going to instantiate S. This will be the ND array object, two-dimensional, which contains the simulated stock price processes. NP, and I go with the zeros to get started with. And now I go with m+1 time steps and I paths. Why m+1 time steps? Yeah, when I speak of 50 intervals, I have 50 plus 1 time steps to consider. So I have 50 intervals, but I need to take into account the 0 as well. So I get started at 0 and I end at 50. That's the idea. And I here for the number of paths, like 10,000 paths with 50 time steps, 51 points in time each. So this is now a large ND array object, and I set the initial values, the starting values, now to S1, because this is simply where we get started, right? When you have a look now, trading hours in the US, have a look at the Apple stock price, you know exactly what the Apple stock price now is. It changes, of course, on a sub-second level slightly, but you basically know what the starting value is. You don't know the value of Apple end of next week or 3 months out. This would be too nice. If we would know that for sure, we wouldn't need to deal here with a Python language, etc. We just simply, invest accordingly and would become billionaires within a very short period of time. So the future is uncertain, but the presence, so it is the assumption here, is well known. It is fixed. The starting value is fixed. But since the future is uncertain, we now use our random numbers. And I do the following. I generate now, let me use my RNG and go with the standard normally distributed values. And I take the same shape as before. Right, the same shape as before. Draw like 51 times 10,000 random numbers to do the simulation. In the next step, that's now the, I would say, the most important one. That's now the simulation part, the core. If you like, I do the following. For T here, for T, sorry, in range, I get started at 1 and I go to m plus 1. I say now that S of T, we start at 1, is S of T minus 1, so the previous price, times NP exponential function. And now, if you have never seen this, just trust me, take it as it is. More details are to be found in quite a few of my books. Python for Finance, in Financial Theory with Python, and Derivatives Analytics with Python. You find a ton of details and more beyond that. But here we simply take it as given. So we do now R minus sigma squared over 2, now times dt. This is what we have calculated up here. Plus, I hate it when the plus is here up front, plus now I have imported math square root of dt times sigma times, now the random numbers come into play. Random numbers, and we take the slice. There was just a question in the in our user forum where the question was why do we multiply here by dt and here we use the square root? Yeah, both the return and the variance scale linearly with time with regard to such a process, but since the variance scales linearly, the volatility which I need here or which I use here scales with the square root of time. So just this was just, I think I answered it today or yesterday maybe. So this should now simulate the path. So now have a look at S. You see we start at 36 and then it goes here over the 50 time steps. So the first point in time or value is fixed and the rest is random. And the further out we go, the more uncertain the values become. So the volatility becomes larger. It scales here with the square root of time. So that's our simulated path. I can, for example, now take out one path only here, let's say the first one. And this would now give me a path starting at 36. And here you see it goes over different values and ending down here. It's easy enough to visualize that. PLT plot. And this is the first simulated path. I can go with the second simulated path, the third simulated path, and so forth. Let me maybe do, this will be the first three. You see they all start at 36 and then randomness sets in. Where we go with 300, for example, you see how it behaves as a total, right? Maybe 300, we don't need 300, maybe 100, because there's a ton of overlay here, right? 100 is enough. It all starts at 36 and towards the end, it's pretty uncertain. It can be well below 30, it can be well above 50 or anything more or less in between. We can also add here the average PLT plot as the overall times the first one, and I take the mean value over axis axis 1, I think. Now always with the axis, it's not like the easiest. Yeah, we see it here, right? Not too good. The mean and with 2. No, let me. What did it do? Line 2D said good style on a style doesn't work. PLT plot. I simply, I mean, it did the correct thing, but I want to show it in a way that we all see it easily. Let me do the LV again, like 5. Yeah, now it's thicker, but not kind of. Do we have a color? Do we have a C argument? I don't know. Yeah, we have a red one. Now we see here the red, which is the mean value, right? This is the mean of the values. You see, overall, the mean value, it's not directly linear, right? But it's roughly like a linear thing, which increases at our rate of 6%, roughly. So we can check that. This is a usual check that I do with regard to Monte Carlo simulation, that I say here the following. I have my simulation. I take the final values, and from that, I take the mean. So this is the forward price of, according to my simulation. The mathematical forward price is S0 times math exponential function R times T. So that's the real forward price, and you see these should be close together. They are not exactly the same in general, but they are close enough for our purposes. And now the question is, how can we do the valuation of a stock price here, right? The valuation of a put option given a certain strike price. Yeah, for a European option, that's a pretty straightforward manner. We have basically all together. The only thing, let me, I need to give it a little bit more structure here, right? So let me do this a bit smaller. So here, and here I say valuing options by MCS, Monte Carlo simulation. So that's the simulation of the stock price process. Here we have the base parameters for the economy, simulating a stock price process. That's all good. That seems to make sense. Here now I say valuing a European put option, and European here is the major thing. We have the strike price, right? It's 40, and the inner value at the end is HNP maximum. We haven't seen this yet, but this is also a vectorized operation, K minus S and 0, right? So we can visualize this as a histogram, H, and we see the payoff of the option at the very end. Something is now pretty slow on my machine. It can't be. With all these values, I need to probably, maybe I need to rerun this thing, or my Docker container has not enough resources. Let me check here, my Docker container, what's going on? Do we have htop? No. Top is there. That's a more simple version of htop. Task 6 total running, CPU, use system ID, used. Yeah, that's quite a bit used. Yeah, but you see here that's I don't have that much free here with regard to what I'm using, so might be the case that I'm simply running out here of resources. And before I do now a large scale analysis, but you can imagine that when we work with all these objects, like 10,000, a million, 100,000 times 50, etc., and we have a bunch of these objects, this eats up memory, yeah, on a, in the end, large scale. Sometimes you have a memory footprint which is simply too large relative to the resources, right? And here in my Docker container, from all my only resources, my resources that I have locally, where's kind of like the, here, let me install install htop. I never ever use the top here. So when I go to htop, you can immediately read it. We get here 4 gigs of RAM and 4 cores. Although I have on my Mac machine, I have 8 cores and 8 gigs of RAM, right? I just get like roughly half of it here, and this might be eaten up much faster than I would like it to happen, and of course faster than what would be on my local machine. So let me, for the time being, switch to my local machine and open the same package here, right? There is the Monte Carlo simulation. So let me now rerun the whole thing. This should also be slightly faster, although it's physically on the same machine. It's of course now natively run on Apple Silicon and not via the container. You see it runs through. So let's see what happens. All the timings take a little while. In the meantime, I was neglecting a little bit the Discord. server. Sorry for that. We have here as well. Now I think the questions so far are all answered. If some questions are open, just let me know. So here you see it's what is the problem here with the histogram of the age? Something weird. No. Oh yeah. Sorry, I see where the problem is. I need to go here with the final value. So this was not about the story that I mentioned before, although that story often enough is a true one, right? But here I now noticed, since I'm now natively, I noticed another issue, and basically this is that I was going over the whole and the array object and not over just the final values, which now executes pretty fast, right? So age and bins 50. So that's a not untypical payoff profile for a European option where you have a ton of realizations, basically the majority out of the money, so 0, and here you have then the in the money expirations. And the valuation now is pretty straightforward. I take the mean value of the inner value, right? This is the inner value, it's the payoff at maturity. I take the mean value and do a discounting, math exponential function minus r times t. So I discount the value from maturity to today so that I get the present value here. Present value MCS estimator, this would be the technical term, estimator for European put option. And that's 3.87, and that's in line, I guess, what is in the paper there. So that's I think that's kind of nice already, because once we have done the preparational work with regard to the simulation, the option valuation is just like one line of code and a second line of code, although we are dealing with hundreds of thousands of values, sometimes with millions of values. Nevertheless, this here is a pretty efficient affair, among others, due to the fact that we are using NumPy. With a pure Python, it's a pretty good exercise. I can only recommend that you do it for yourself with pure Python, so that you even better become aware of the advantages and differences between NumPy and pure Python for these applications. So that's the first value. So now for the American option, we need regression techniques. Therefore here, excursion OLS regression, right? Before I get to the American option case, like here, let me put this as a marker, valuing American put option. Right, here we did the simulation. Here we valued a European put option, and here I can also say an American put option. But to do the American put option valuation, we need ordinarily scarce regression. Therefore, I want to do a little excursion. And the excursion should be as follows. I pick out a random stock price path. So all the time, all the points in time, and let's say, I don't know, 10, for example. I can change it if I don't like the use case. So PLT plot, we have done so already, and such a single path is visualized. And I now want to do a linear regression, a quadratic regression, and a cubic regression to approximate here the evolution of the simulated stock price. price. And to this end, I have, and let me choose here N, so that I can later on change it if I like. And I can now do the following. I can do rec. This will give me the result, NP poly fit. This is now the regression step itself, right? NP range, or let me define this once. Oh, what did I do? What did I do? I was pressing the wrong key. Here the X values shall be NP range M plus 1, that I can reuse them, so don't need to repeat it. I poly fit X against my stock price, here lowercase n, and the degree for the regression shall be 1, so linear regression. Linear regression. What I get are parameters for linear regression, ordinate value plus the slope. That's the ordinate value here, and that's the slope. So I can now do the visualization as follows. I can repeat this here and can plot PLT plot, and I plot now NP polyval X, rec and X. Rec must come first here. So my regression parameters plus the X values. Right, and you see something that should be well known to you, like a linear. I mean, to regress something linear, with a bit of experience, you know how the line should look like. I'm pretty sure that if we were supposed to draw a line through such a chart, we wouldn't be that far off from the mathematical solution in the end. So that's now a linear regression. So label linear regression PLT legend. So linear is green. Let me add now. I do here reg 1, here reg 2, Now I do a quadratic regression. Quadratic regression level 2. So I need to re-execute it to have the parameters available. Reg 1 is linear, and reg 2 now gives me the quadratic regression, which looks different. Now in red here, and it is like, it's not linear anymore. It's kind of like part of a quadratic function here. We can go one step further and do a cubic one, which is for what I'm planning to do, kind of like already a good level, a good degree, 3, third degree for the regression, quadratic should be a C, and here we go with a cubic, third level. And of course, I need to plot this as well. All right, 3 cubic. It's now the what is that? Purple, right? It's the purple one where you see, this gets the shape kind of nicely, better than the other two, right? But it's not my major purpose whether this is good or bad. And just to show you that, maybe let's go with the 11. And when you do this, you will see completely different paths, right? So now that's a good one. This is now a decreasing one, right? The stock price drops And let us see what happens here. Yeah, the linear regression goes down, down, down. The cubic and the quadratic ones are not too different here in this case. So this is now pretty easy and straightforward. Maybe let's do one more, like number 12. That's a sidewards case. This is probably not that interesting because, yeah, this is what I would have expected. Like they are more or less kind of like the same. So the green line almost horizontal and the other two more or less the same. Again, if you do this, if you repeat this, I haven't fixed any seeds here, you will see completely different cases. Maybe one final one, and then I stick to that no matter how it looks. This is an upwards going one. And here we see the results. So that's regression. You see also NumPy. NumPy provides polyfit and polyval. These are helper functions for univariate regression. You see, it's pretty straightforward and comfortable to use these and to visualize them. But I don't want to do a visualization of what is to come. I want to use regression in order to to implement the least squares Monte Carlo algorithm. And for that algorithm, I use the regression approach that we have just seen. So, based on the least squares Monte Carlo, abbreviated LSM algorithm by Longstaff Ward's paper was published in 2001, and it's one of the major breakthrough papers in numerical quant finance, I would say. Because if you think of it, I mean, it's 20 years. This is long, but not that long. I mean, 50 years before that, people were valuing options. Since the 70s, Black-Scholes was there, but there was no algorithm up until they published their algorithm, or no efficient algorithm, let's say, which allowed the valuation of American options, put options in particular, with early exercise by Monte Carlo simulation. So this took like 30 more years after Black-Scholes until this problem for Monte Carlo simulation was solved. So what do we have now here? We have the fundamentals together. What I need later on is a discount factor, df, and that's the following. That's math, exponential function, r times dt, but it's a discount factor, so minus r times dt. So that's a pretty small value. It's a small discounting effect, let's say. It's pretty close to 1, as we see here. So that's for our period dt. That's the discounting factor. So that's that one. So what else do we need? I get started, and without diving into the theory of valuing American options and an early exercise and all the elements, I just want to focus here on the Python side of things. I have the value of the American option at the beginning, which means at the very end here, equal to the inner value of the option. Therefore, I go here with h of -1, which gives me the final values here for h. So that's the starting point. And now I go, or let me put this into the same cell here. Now I iterate backwards. How do I do that? Backwards. Before the simulation was forwards, right? We did the propagation forwards. Now we do a backwards propagation. So we start at the end. So for t in range m, we go until 1, so 0, because 0 is excluded, and I go backwards. You haven't seen this, at least not in our bootcamp here. I can use range also backwards. So when I evaluate this part here, you see it's like 50, 49, 48, etc. Right? And I should, now that I see it, sometimes it's good to see this explicitly. I'm not starting at 50 because I have my V value already. So I would rather start at m-1 at 49. And what do I do there now? Yeah, I do the following regression. So, and now this is where NP polyval from before comes into play. I regress the stock price at T against the value, the future value of the option V that I discount. This is where DF comes into play, discounted by one time step, and I choose a degree of 3. I said cubic is already a good element. I calculate now the continuation value, capital C, via NP polyval rec and S of T. So this gives me a continuation value. If you have never heard about continuation values, inner values, option pricing, see it as an exercise in applying regression analysis and simulation to a financial problem there. The continuation value. So this is now used to do the following. The new value of the option is now overwritten, but we get started at the very end. Now we are at T, which is m-1, is now NP where, and I check now whether the inner value at T is greater than the continuation value that I've just estimated. If that's the case, I set the inner value. Otherwise, I go with the real continuation value. So the whole, that's kind of like the core of the whole paper. This was a breakthrough, and it took researchers decades until this problem was satisfactorily solved. But it's like with many things, not with all things, but with many things, once you have them, they look so simple and straightforward. And to come up with the value now, I would calculate the mean here and would do one more discounting. So what do we have? Polyval, of course, is wrong. I need polyfit. Polyfit and polyval. These are the two. Now I have another error. Let's check expected 1 layer 2 array for that's that one. Where do we have h of t? There is some dimensions going wrong. Which one is it? Which one is it? ST. What is we? Let me briefly check what how these things look. Right? We is simply a value of h. Yeah. Why is h just one value? Yeah, of course. So sorry for that. I was still working with the h here from the European option, right? But now I need indeed the inner value, which must be a matrix for the American option. So here it's a vector only, but for my American option valuation, I need a matrix. Dimensions are sometimes pretty subtle. So here I need what I was writing before, but there it was wrong. Maximum k minus s and not s of something, right? And now we get the algorithm correct. So the difference was here we have a matrix. Before we just worked with the final slice. Here we work with the whole matrix. That's the major difference. But the matrix simply here is required because now we have V as a vector, and this is what we need, V for the value. Right? Yeah, that's now the option. And the value according to the paper, I mean, we can Google that paper. Longstoff-Schwartz, I probably have it here. Longstoff-Schwartz, American option pricing here. There are a few more bookmarks. But you find this paper that I mean on the web here, valuing American options by simulation, a simple least squares approach. And in that paper, they introduced the algorithm that I've just implemented with a regression, that's ordinary squares, least squares approach. And I was writing my PhD about one paper of Schwartz, Eduardo Schwartz. I met him personally. It was a great event. And I said, I spent like, it feels like years on end with stuff that Eduardo Schwartz has been working on with different co-authors. And here we go again. Also, the papers, one of the reasons I should mention why that's the case, what I was mentioning before, is that he writes and they write pretty good papers with well explained examples, etc. So I want to scroll down to table number 1. There comes a point in that paper, we skip over all the theory here behind it. Well, where do we go? Here are the numerical examples. That's table 1 in the paper, and let's see whether we find the parameters. Here you see S36, this is my S0, sigma is the volatility, 20%, T is the time horizon majority, and down there you find the rest, like the short rate, 6%, the strike price, 40, yeah, that should be almost it. And the European value here, closed form, this can be calculated obviously with Black Scholes. It's 3.8. Let's briefly check. 3.8 for the European value. This was up there, yeah, 3.8768 something. So that's the value that we came up with. And in their paper, they're at 3.844. So we are slightly above it. For the American option, via finite difference, they report a value of 4478, or here simulated with the LSM approach, 4472. We come up with 4.41. That's still a little bit on the lower end, and the estimator here is a low estimator, meaning the value that you get here is supposed to be, it's always lower than the real value. So we would expect it to be lower than the real value, but not that low probably. So for example, when I go with degree 5 here, you see immediately the value increases already. So the higher the degree, it's not necessarily be the case. 7, even a bit higher. Now it's slightly above. We can now go and do more simulations, go with more time steps. Everything will, in general, so generally speaking, improve the performance and the accuracy of the algorithm. Of course, when I redo the simulation, so here, when I redo the simulation of the paths with the random numbers, of course, oh, I was typing the wrong thing, sorry, using the wrong shortcut. Going with X for me, with a shortcut down here, that's an interesting case, like linear, quadratic, cubic, the same. I've now redone the simulation, and you see after that, instead of 4.45, we get here 4.39. It's all in the ballpark, so was not my intention to come up here with an algorithm as exact as possible. If you are interested in an algorithm, please read my book, Derivatives Analytics with Python. You don't even need to read. You can go to the GitHub page of the book. There you find a ton of code and many examples that are dealing here with the accuracy and the convergence of that algorithm in that simple case and in more elaborate cases. Yeah, Monte Carlo simulation, NumPy here. For me, that's kind of like a combination made in heaven. Yeah, let me restart the kernel and refresh it. Just checking for the questions. So far, we have no other questions. I can then push the current state to the gist. In the meantime, maybe copy my duplicate, copy my empty notebooks. I have one left over after that. Here, the next Jupyter notebook. is open, but it's still fresh and empty, right? Let me close that, maybe also shut down the kernel. Here, now I'm on my local machine, but you see there is hardly any difference, and there was just the hiccup with the visualization of the inner values where I was on the wrong path. But you see, I can change here Jupyter Lab, my Docker container, or my local installation. It doesn't make a difference. I'm pretty sure you don't notice any. I don't. I even need to have a careful look here at the instance with which I'm working. So for the remainder of today's session, I want to revisit our example with the financial data, right? Before we revisit that, I want to show you that we have in NumPy also structured arrays. And what are structured arrays? I introduced NumPy SNP. I introduced NumPy by saying, yeah, list objects are flexible. We can have integers, floats, strings, and even list objects with a regular ND array object. Like now I use linspace just to have shown it. Linspace, it's a pretty nice thing. I can say, for example, 0, or let's do 15 out of the box. It will give us, yeah, let me do like 0, 15. It will give us evenly spaced intervals. So I was not putting the starting value in here. 15 was supposed to be the end value. Evenly spaced intervals. Maybe I don't go that far. I can, or that many. Maybe I go just with 20, for example. This gives me a smaller amount. So evenly spaced intervals, like our time slices that we have been working with before. So, and I was saying that a D type here is for a regular ND array object, regular ND array object has a single D type. So if we have a billion numbers, it's float or integer, or we can have a billion characters, strings as well. But here, that's the default value. And everything that we have been doing was with numbers. One-dimensional, two-dimensional, simply numbers, right? But we can have something else. We can have structured arrays. And let me make a simple example. And let me get started with some yeah, they're called records. I call them now here, or I construct them as a tuple. A tuple, like you recall my example, like 1 and 2.5, and maybe a string like A, let's say, right? Then I can have another one like 2 and 3.5 and B. It's another record. Then let's do a third one, 3, 4.5, and C. So that's a typical tuple: integer, float, and string. And we can use these tuples now, or as they're also called, records, to construct a structured array. Let us try this. So NP array, now I use the square brackets, T1, T2, T3. So what does it do? It accepts what I was passing, right? So no complaining, oh, there's integers, floats, and strings and whatnot. What it does by default, you can see it here, is, yeah, it takes the data type, the D type, which can accommodate everything else. So the integers and the floating point numbers are simply converted to string objects. With a string, we can have an ND array object with strings only. So that's what we see here. But that's not what we probably would like to have when we do this, right? We probably would like to have conservation of the types here that we have integers, floats, where we might do some calculations, and here we have the strings, right? So therefore we can define a D type like NP array T1, T2, T3, and now the D type, let me see, yeah, I think I should be able to write it, the integer 8, float 8, and object. And this works now. So now you might say, well, Eve, well, the string is kind of cryptic. Yeah, it is cryptic, but I for integer and F for float, I think it's not that special. Here I only say, well, just use 8 bits, right? Here, and here O, capital O stands for object, which accommodates everything. And this is here like the string, the least common denominator, right? And you might say, well, what is this now about? Yeah, the first thing is that we have achieved one of the goals, that we want to preserve here the type of the single values, right? When we want to do addition, numerical addition, we have transformed everything to characters. This doesn't work anymore, right? But now we still have this. Conserve. So let me here like structured array as A, for example, as A. Or I can do the following. I can go with NP, or let me write it in a different line. DT for D type, NP D type. And now I go here with the dictionary approach, where I say names, and the names are lists. I now make life easy, X, Y, Z, for example, and the formats are like I have here, for example. Sorry, here, yeah, that's the equal sign, of course, must be a colon. Yeah, this doesn't work. I was expecting this, but I had some other mistakes there. So I need to write it that way. It's a bit more writing. I thought I could go with a shortcut. Like here, so in certain, you see here it accepts the shortcut with a string. Here, when I go with the dictionary approach, I need to provide this as a list. So I must confess, I hardly ever work with structured arrays. Other people probably neither. So, but they are still pretty powerful in certain contexts. They are pretty helpful. So now that I have this D type, let me print it out, this D type, you see the internal representation, or now what we see here, looks quite a bit different, but this, for the time being, is not our major concern. I can hopefully use this now here and pass it to the constructor, which seems to work. And now I have the D type here, where I have names, as it's called, formats. Formats are the same as before, but I have my own names. Before, names were simply given. And why do I emphasize this now? Yeah, because I have now access methods which go, for example, like this, where I go S of capital X and I get just the integers, right? I go with the column Y, I get my floats. And I go with the column set and I get my strings here. I mean, the single characters, but they are strings, right? I can do now things like here, take the mean value, which should be 2, right? I can do calculations now over columns by naming the columns and then calling the methods here. What else can I do? I can also go and say SA. Let's try the regular indexing. Yeah, this also works. I get back my T1 tuple, my first record. Or I can go here to 2 and I get back like 2, which is again a structured array. Like this, right? The second tuple, 2, 3.5, and B, or a selection of it. So you might notice that this might be helpful, in particular when you are dealing with data, where you want to have the benefits of NumPy that we have discussed so far, but you have different D types that you need to accommodate. And this is where structured arrays come into play. And why do I introduce this? Yeah, because I said I want to get back to our example with the financial data, the real financial data, end of day historical data for Apple and Euro, US dollar, S&P 500, etc. And when I want to work with such a data set with NumPy, then structured arrays are my friend. That's the reason why I've introduced them now in a pretty general and simple fashion, but we can do much more. So let's see what we can do with it. So the financial data itself. First, we need the data, right? I need to retrieve it, and I use requests as I did before. And the text form is retrieved by requests. Get, maybe I define it here, the URL certificate tpq.io eudcsv. No, it's fin data. You know, I have a few of them, but that's the more recent one. Get the URL and the text word. So I can chain this. And when I did it for the first time, I did it step by step. But now I get my complete text that I have retrieved. I mean, CSV, it's just by convention. Requests and Python at this stage doesn't know that this is a comma separated value file. This could also be a text file, a poem, or financial report, whatever. Only since we give it meaning through the comma separated value approach, it is for us something special, and we treat it now as something special by processing it in a special way. So the first 1,000. So I have this now in memory for what follows. I'm going to write it first on disk. So with F, with open file, and I call this data CSV, or let me call it fin data, or let me call it data, so that we really know this is the remote data set. This will be the local one. And I open this file for writing as F. I simply write, I dump the whole thing that I have, the text, to disk. You see immediately here it appears on the left-hand side. When I open this with Jupyter Lab, you see here this grid. Jupyter Lab can nicely represent CSV files, like Microsoft Excel can, like numbers on Apple can, like Google Spreadsheets can. You see this here now visualized, right? So with our columns in a nice tabular form, we have the date column here, which we know is special. The rest are prices. We have incomplete data. Here we just have, for example, for the very first day, 1st of January, we have Euro US dollar quote, and here we have the gold quote, but nothing else on that date. So easy to inspect this standard data form. So that's the financial data. And now I want to import the data. Importing the data with NumPy. And we have a function for that, which is called gen from txt. That's the one that we are looking for. So when I now open here parentheses and pass in the name, let me see what happens. I get not a number value is not a number value. So that's not satisfactory. So what I need to specify here is the delimiter. This is supposed to be here, the comma, because it's a comma separated value file. But don't trust the endings of files. There often is the case that that's the reason why you can almost always parameterize this specific element. Even if it says .csv, often you see like semicolons or comma and a blank or whatever. I have seen so many things in my Python lifetime, right? It's basically uncountable. So now suddenly it looks different. We have a ton of nons, and then we have nons and some values, and maybe we are closing in here. So that doesn't look too bad. So I want to go through this step by step. So one additional element that I can specify here is the D type, and I should, by default, it assumes a D type of float, but I set it to none. Then it tries to judge the D type. So here it's now saying reading Unicode strings without specifying the encoding argument is deprecated. Set the encoding, use none for the system default. Okay, I can live with that. Here encoding and coding, I also set it to none. And now we have, well, what do we have? We have here the headers, right? And we have then some dates, and everything here is a string, right? So I don't know if this is kind of like the desired output yet. I would say no, but at least with a few tweaks here, we were able to see something that is meaningful and that somehow fits what we intend here, right? So that's for sure. But it's, I would say, thinking back of what we've been doing with Python, with pure Python, this is like the third step or something, right? But just that we have an array here with only string objects and not values or nothing. So we haven't gained that much. Now let's add a few more tricks here. And one more is, maybe let me break it here, is that we say names true. You recall I have used names up here when I did that one here, names, right? Names list true. And by default, when I put in gen from text names true, then it looks in the first row by default and tries to figure out what the column headers are. And here, indeed, we know, we have inspected the data, that the first row is about the column headers, right? And therefore, names true. I would hope that we get now a slightly different case. And you see already, it looks completely different. Now, just by setting names to true, we suddenly have here a proper D type. We are only now we have arrived, if you like, at a structured array. So this here gives let me write it that way, gives a regular array with a single D type. This here now gives a structured array, or any array object we would like to write it out. Right? The different D types. Here we have the date, right? Still as strings, and we have Apple, Microsoft, and these obviously are all floating point numbers. So in that context, I could already work with let's say only with the Apple data here, right? And say, give me the Apple column or whatnot. Maybe I do this here, structured array or data. Let me call it data here. Data, but I show it here with data if I'm interested in Apple only. So you might notice it has deleted all the dots. This was AAPL.O, but I think that's fine. And I get just the Apple data. Or to the same purpose, I could go with euro yes, dollar, euro equal sign, but the equal sign was probably dropped here as well. Yeah, the equal sign was also dropped. That's all good as it is, and I can, for example, do PLT plot data euro, US dollar. There's not that more, and I can from data euro. I haven't imported it from Pilot. Yeah, this was in the other notebook. Import PLT. Let me now open with my configurations. Don't want to type it out. A little bit lazy towards the end of today's session. Where do we have the config one here exactly? It's technical stuff there. Importing the plotting and the minimal configuration. We see here now the euro US dollar. We have done a plot like this with pure Python. Here it's now from the structured ND array, where we have just taken euro US dollar out of the original data set. When I go with Apple, looks the same, but if you pay careful attention, we have not the number values, and they are shown here as discontinuities, right? If you need to pay careful attention, there are a few of these where there is no data for Apple. With a euro US dollar, we wouldn't spot that, so I might leave it here with, or the other one looks more interesting, or whatever this means, right? So that's it. So what we did with the plotting, where I said, well, this all looks nice, but we don't have time information on the x-axis, and this is what I want to accomplish here. And yeah, I would say that's maybe the final thing that we do for today. This was my goal to come to that point, but in between I always check no questions. I hope when there are no questions, or just few questions, I hope that's a good sign and not a bad one. Feel free to ask questions anytime, as good as I can. I will answer them. But my goal is to replicate the last step here in the context of the structured ND array object, meaning that we have here the date information, but still as strings. And you might recall what we use, like we use this function from date time to do the conversion, and we can apply something similar here, but I would need to use that one here, and I can define converters. So my CF function should be as follows: lambda x, this should be, let me import date time, lambda x should be as follows: date time dot date time string p time, the date, and then the format. We had we need a capital Y, the %m and dash %day here, and I can now use here converters, and set now the converters as follows. I specify the column, and that's here the, must be the, it's the 0th column, right? The 0th column, and this shall be changed according to CF. Let's see if this works. I'm not sure CF is not defined. Yeah, I need to execute it. Name error, where's the name error? Date is not defined. Where do I write? X. Of course, lambda X and X. So this X must repeat here. That was the problem. Oh, it seems to work out of the box. I wasn't sure whether 0 or whatnot. When I now have a look at data, you see now we have data represented now here as date time objects. You see here date time 2013, 1st of January 00. So there is no time information, no hour nor minutes. But instead of just strings, we now have proper representation. And the technical conversion was the same as we did with pure Python, but here we do it in the context of reading data from a CSV file and converting it via this custom-made function here, which I can use via the converters parameter. Here where I say the first column shall be converted according to CF. According to this function. You see, just like a few parameters, and now I would say, in a pretty comfortable position to read more or less any type of such end-of-day historical time series data. It could be, for example, open, high, low, close, or whatever comes to mind. It could also be minute bars. Nobody says that we need to stick to end-of-day data. Minute bars, other intraday, even tick data, etc. would now be readable if the basic structure is in principle like what we have here. So with that data now, I can do a visualization like this, PLT plot. Now I go with data date, that's the name, and data, maybe let's do some like the gold quote, for example. How we get the gold for an ounce of gold over time here, the visualization with the years properly displayed here. I'm always inclined to do some experiments at the end, but I think that's that should be good enough now with the structured arrays, where we have one means, one way, one blueprint, let's say, one framework to import CSV data. And there are other, of course, there could be other sources, but the CSV is still the least common denominator in the financial world for data exchange. And most of the applications can export data as CSV. And when you have such data, here, there's a way to get the data into a structured ND array and then to have all the advantages. And by all the advantages, I mean something like data, and you pick out euro, US dollar. This was one of our examples, and I simply calculate the mean value much faster and much more convenient. Or if I like, for example, the standard deviation, right? I can do that here as well, right? Or I can calculate the log returns, right? The log returns as follows: NP log without iterating, and I take the data log return depending on what. Let's say the euro US dollar we take here, but we only take it from 1 onwards, and in vectorized fashion I divide it by -1 excluded. So in vectorized fashion, and then PLT histogram log return the bins 50, and I visualize the log returns here for the which instrument did I choose for euro US dollar? I think something that we've calculated before as well. All right. So with NumPy, we have all the power at our hand. We have the speed, we have the luxury of vectorized operations, where we don't need to write loops, where we have much faster execution. I mean, admittedly, 2,500 points, data points are not that many. So there are much larger data sets, but if you get, let's say, into tick data, or you want to crunch numbers for 1,000 different instruments, what many people do in the real world, then you might be happy about the speed advantages on top of the convenience benefits that we have in terms of the vectorized operations. Yeah, in that sense, no questions open, just on time. This final step wasn't on my mental map, but doesn't hurt to see the calculation here in vectorized fashion and visualization for the log returns. You have it all in the gist now. NumPy and the array objects, random numbers, visualization, option valuation of European as well as American options here, Monte Carlo simulation, financial applications. We have done a bit of statistics with regard to the regression, and maybe we come to machine learning and vectorized backtesting as examples with pandas, because when we revisit the case of importing the data with pandas, this is a one-liner with 2 parameters, so there's not that much to say. That's one of the benefits of pandas, but there are other benefits as well. But for the time being, I would say let's wrap up today's session. You have seen hopefully the power of NumPy and the benefits, and yeah, I'm pretty sure you have a couple of use cases that might jump to your mind. Let me know about them and also about your experiences. I wish you happy Python for finance coding as well as NumPy usage. Pretty fast, like our German cars, right? And I'll see you in the next session. Take care. Bye-bye.